Team 7. My name is Hector.
I'm Juan.
And I'm Bruno.
We got to talk about a 4-bar mechanism and a synthesis of a slider crank. The first project is the 4-bar mechanism. We can see we got the given constraints, R1, R2, R3, and R4, and the angle, the input theta 1. Our inputs are theta 4, omega 4, and alpha 4, as well as the coupler link length and the beta, the angle for the coupler link. After doing the calculations, we conclude that this is a type 2 mechanism, so it will always be a double rocker system. Now Bruno is going to talk about the coupler position.
Okay, here we have a model with a QS distance, which is the link length from the joint 2 and point S. It has a beta angle of 40 degrees. The QS position trajectory. Here from this model on SolidWorks, we can see the path that the model did, which is pretty similar to the one done on paper and on Excel. Here are some graphs comparing the angular velocity and position, and acceleration and position. This is an actual mechanism of a double rocker. It's a gas pedal moving a rod, which is moving a little lever that allows air to flow into a carburetor of a gas combustion engine. Here's a video of the double rocker making its path. Here for the conclusion, I'll let Juan explain.
All right, for this experiment, we saw that we had two different closures that we were able to find for the joint motions, which was theta 2 and theta 3. And a position of a trajectory of S was graphed through SolidWorks and Excel, and both of the graphs came out pretty much equivalent. And also through kinematic equations, we were able to analyze all the angular accelerations and angular velocities, which were between 114 degrees to 307 degrees roughly. And the values before and after that were all imaginary values that didn't work for our system since it was a double rocker. All right, now we're going to talk about the synthesis of a slider crank mechanism. The slider crank mechanism, we were given 3 points of A and B that the coupler link went through. We used those points to find AO, which helped us find our circle of slides, which we found P1, P2, P12, P13, and P23, which were our pole positions for our circle of slides, which gave us P23 prime, which then we were able to use to find C1, C2, and C3, which gave us our circle of slides, which gave us our slider line, which is where the actual slider crank actually goes along, which is parallel to R1, right? Using that, I have Bruno to talk about the slider crank design.
Here we have another model, this time of a slider crank. We can see the box sliding on the plane. This slider crank can turn 360 degrees. This actual model was done representing an electric saw. So it's basically an electric engine spinning a little disc, making a circular motion that is going to be translated into a linear motion for the blade of the saw to be able to cut. Here we have the model drawn in SolidWorks, where we have the circular motion, which will be turned into a linear motion and giving the blade this linear motion for it to be able to cut any material like wood or metal. On the conclusion, I'll let back Hector finish.
After doing all the analysis of the data, we came to the conclusion that this system satisfies all the initial constraints, so we were able to design this system.